In this presentation, we're going to discuss about Windows Memory Management Part 1. Basically, we will be dealing with kernel mode and user mode in Windows. We will be understanding how security is implemented in Windows operating system or any modern protected mode operating system. So this is a little bit of a roadmap of the presentation series on memory management. So today's topic is mostly protected mode and paging, which is basically segmentation and paging. We'll be concentrating on 32-bit Intel architecture, which is the x86 architecture. Physical address extension or the PAE is turned off to avoid complications when we resolve addresses, virtual addresses to physical address, etc. So this presentation is not completely for beginners. So understanding of C or assembly programming language is required. So we won't be explaining basic registers and things like that. We'll be directly going into control registers and advanced CPU configuration, if you will. So let's try to understand protected mode in modern operating systems. So what is protection? Do not allow a program or a user mode program to access or modify other programs' data in a multitasking environment. So that is one of the major goals of protection. Also, at the same time, do not allow a program to access or modify the operating system data. Again, a program should not access system hardware resources directly, like mouse, keyboard, monitor, or any other devices like that. That is also should be protected from a user mode application. Only kernel or the privileged code should have access to those resources. So how protection is normally implemented? Normally it is practically impossible to implement protection by an operating system without the assistance from the CPU. So certain platform does that, like virtual machines like Java, .NET, etc. We are not going to discuss that here. We will be dealing with hardware assisted protection today, specifically on x86 Intel architecture. Modern operating system like Windows or Linux uses CPU feature called paging and segmentation to implement protection. Modern operating system always work in protected mode of the CPU. So they have something called privileged mode and they have something called user mode, which is the non-privileged mode where the normal application runs. So when it comes to x86 protection architecture, mainly operating system uses segmentation and paging, two features of CPU as I mentioned before. Segmentation is practically turned off using flat model, which we're gonna discuss later. Segmentation is a feature in the CPU which you cannot turn off once you are in the protected mode. Again, we will see this through this presentation. So following is the abstract working of protection. Any security system has following attributes: an identity verification mechanism, a check or verification of the above mentioned identity, access to a particular privileged resource if above check is success and otherwise no access. So let's see some examples. So let's consider an airport. The identity verification mechanism in an airport is your passport, basically, in most of the countries. A check or verification of the above identity is the checking of your visa stamp in the passport or the type of the passport by the government authorities in the airport. Another example is your swiping card to a company. So you have an identity card. You swipe that identity card somewhere, there is a checkpoint, and the door get opens if things works. Otherwise the door won't get open. We have a couple of implicit points here. You cannot make a passport and stamp a visa by yourself, but the visa is issued by the country you are going. Likewise, you cannot make the ID card by yourself, but it is issued by the company for which the access is needed. So this is a very important point. So this is the core of the security. We'll see the implication of these points later. So following is the abstract working of protection in a generic protected mode CPU. So the identity verification mechanism is a value in a special register in the CPU which designate the privilege of the code which is currently being executed. Now next thing is the check or the verification of the above identity is the check inside the CPU for each instruction. So this happens in the CPU circuitry, which checks the instruction which is being executed. While each instruction is being executed, it checks the above mentioned special register value. So now the access is granted based on the success or failure of the check which is just performed. The execution of the instruction is succeeded and the resource access is provided if the above check by the CPU is success. Otherwise, an exception is thrown or an interrupt is happened and the control goes to an interrupt handler or an exception handler installed by the operating system. This is like the visa is not correct and it goes to the authorities for further investigation. So just in the case of ID card and the passport, this so-called special register cannot be modified by a less privileged program, just like we cannot issue a visa or ID card by ourselves. There is a region of memory and a class of instruction for the CPU which needs a special value in a special register in the CPU to access and execute respectively. The special register can be modified only if you have special value inside the above mentioned special register. If the above mentioned special register do not have that special value and trying to access one of the privileged region of memory or execute a privileged class of instruction, an exception is generated and the control is passed to the privileged card to handle the situation and mostly terminate the unprivileged card which is trying to access or execute this privileged artifacts. So that was the abstract working of a generic protected mode CPU architecture. Now let's have a concrete discussion about Intel architecture for 32-bit platform. So this leads us to the control registers of Intel CPU. So they are like switches of a TV. They can turn on and off different features. 32-bit memory locations inside the CPU. So they are just like other registers. They are 32-bit memory locations. Just like other registers, instruction can modify those registers as well. So in the case of protection, we use control registers to turn it on and off, as we're gonna see later. So following are the control registers we are interested in this particular presentation. CR0 or control register 0. Bit 0 of CR0 register is the bit which enable or disable segmentation. The next bit we are interested is the 31st bit of CR0. It enable or disable paging in an Intel x86 CPU. This is the last bit in the CR0. So the first bit and the last bit is of our interest. Now the CR3 register is also of our interest. Once the paging is enabled, CR3 points to the page table directory base address. Now segmentation. Segmentation is the root of security and protection in Intel CPU. Segmentation works with segment descriptors, segment registers, global descriptor table register, and local descriptor table register or LDTR and GDTR. Segment registers index into the descriptor tables which contains the segment descriptors. GDTR and LDTR point to the base of the descriptor tables. Segment descriptors are 8-byte data structures in the memory which has base limit, protection information and other bits. In a segment descriptor, by setting the base to 0 and limit to 4 GB will be effectively turn off segmentation. But still the protection provided by segmentation can be used as explained in the rest of the presentation. Windows does not use segmentation in the traditional sense to access memory using the base colon offset format, but just for security or protection. As mentioned earlier, to enable segmentation and paging, following 2 bits in the CR0 register in the CPU should be set. Bit number 0 and bit number 31. Now the special register we were mentioning in the abstract discussion of security is called chord segment register in Intel x86 platform. Chord segment has two different potentially unrelated security attributes or bits associated with it. One is called RPL or requested privilege level, which is the last two least significant bits of the value in the CS register. The second one is the current privilege level or CPL, which is the two flag bits in the 8-byte segment descriptor indexed by the 13 most significant bits in the 16-bit chord segment register. In Windows, we use mainly two chord segment values, one for privileged and one for non-privileged. In both cases, RPL is always equal to CPL. But for curiosity, if RPL is not equal to CPL, the minimum privilege among them is considered by the CPU, which is the larger value by number. For the rest of the presentation, we'll be using current privilege level or CPL, as RPL and CPL is going to be the same. So now let's try to understand what is CPL. CPL is a 2-bit number which decides and determines the privilege level of the instruction currently pointed by the EIP register. As it is 2-bit, it can be 0, 1, 2 or 3, which are also called rings of protection. 0 is the most privileged level or kernel mode, and 3 is the least privileged level or user mode. Windows uses only 0 and 3, and when the CPL equal to 0, we say that code is executing in kernel mode. And when the CPL is 3, we say that the code is executing in a user mode in Windows. GDTR and LDTR. GDTR is a register in Intel CPU or global descriptor table register, which contains address of the global descriptor table. So it is a 48-bit register. Unlike other registers, it's 48-bit. It's not 32-bit. The upper 16-bit we don't consider much here because it's not relevant to our presentation. But the lower 32-bit contains the base address of the GDT, as I mentioned above. Now, the 13 most significant bits or MSBs of 16-bit CX register index into descriptor table. As I mentioned, the 2-bit LSB of CS is the RPL. Now, what about remaining 1 bit? It decides whether the indexing is going into LDT or GDT. So this is the pictorial representation of what I have been discussing. So this bottom rectangle is the CPU, which contains the registers. This is the GDTR, and this is the chord segment register, and this is the LDTR, which is not relevant to us. So as you can see, GDTR contains GDT based address. So this is an address which is pointing to some location in the memory. So where it is pointing in the memory? It is pointing to the global descriptor table base. So this is where it is pointing. So this is a table of descriptors. So table of 8-byte entries. So each entry is 8 bytes. So GDT contains a base address. So the chord segment register has the GDT index. So this is the first, or the MSB, most significant 13 bits of CS register. So the third bit will tell us whether this index is of GDT or LDT. So in our case, it's always GDT. Each descriptor in the global descriptor table, which is in the memory, has this many components. So it has the base, then the limit, and the protection or the privilege it has, and some other flags. So this many things are in the CPU: the GDTR, LDTR, CS register, they are all inside the CPU, and all the tables, the GDT, LDT, which is the descriptor tables, they are all in the memory. So this is the view of the 8-byte segment descriptor. So the first 16 bits of the segment descriptor is the first part of segment limit. The second part of the segment limit is here. Now comes the base address. So the base address, first part is the second 2 byte, then here is the next byte, here is the next byte. So base address is a 32-bit value. The limit, on the other hand, it's not a 32-bit value, so it's a little bit less than that. So there is a multiplication factor in the descriptor, so there is a bit actually which multiplies and make the segment limit into 4 GB. So this is the most important part for us, which is the CPL. It is basically the 13th and 14th bits in the second D word of the segment descriptor. So basically, segment descriptor points to a chunk of memory designated by the base address and the segment limit. And the privilege of that chunk of memory designated by the segment limit and the base address determined by the CPL of the segment descriptor. So we have not discussed how security works. All we have seen is some jargons and some bits in the processor. Only if we discuss paging, it makes sense discussing the working of security with all these flags in picture. So now we will see a demo of what we have discussed so far. So we'll keep this diagram handy. So our demo setup is a Windows 8 operating system which is running on a VM player is attached to a kernel debugger. So this is the debugger, this is the operating system. So currently the OS is running, as you can see here. Now what I'm going to do is I'm going to break into the debugger. So I have broken into the debugger. So the first and most important command we need is R to see the registers. So in this we are interested in the chord segment, which is 0008 in hex. Now one more register we are interested is RGDTR. So this is the value of GDTR. So this is the first 32-bit of GDTR. So this is what we need. So this is the base address of the descriptor table. So to dump out the descriptor table, the command I'm going to use is db then the GDTR. So this is how the raw look of descriptor table. So this is how descriptor table looks like. So this is the first entry. You can see that the first entry is all zeros. Then this is the second entry. So it's 8 bytes. So 1 byte is this. Like that, 8 bytes. 1, 2, 3, 4, 5, 6, 7, 8. So it's an 8-byte entry. So like that, you have another 8 byte here, etc. So now which one we have to choose? So that is where the value of the card segment comes into the picture. So let's try to understand the code segment. So to convert it into binary, I'm going to use the command .format 8. So these are the 16 bit in the card segment. So the first 2 bits, which is the RPL, is 00, which means that the code is currently running in kernel mode. So that 2 bits are 00. This bit is 0, which means that this value is indexing into global descriptor table and not to local descriptor table. So if it was local descriptor table, this bit would have been 1. So now this is 1. So this is binary 1, which is also hex 1, numerical 1, all 1. Which means that this is the 0th index and this is the first index. So this card segment is indexing into the global descriptor table, and this is that particular value which we are interested in. Now let's try to understand this value with the help of diagram which we have seen before. So this is a diagram we are using to decrypt the hex value we are seeing here, the highlighted hex value. So the first 2 byte is segment limit 0 to 15, which means that so this 2 byte is segment limit 0 to 15. So that is FFF. Now if you skip 4 bytes, 1, 2, 3 and 4, the next 4 bits is the rest of the segment limit. So which means I'm skipping 4 and I'm taking the first nibble of the second last byte, which is this. So pretty much our segment limit is 4F and this F. Now comes the base address. Base address is 1, 2, 3, 4, 5, 6, 7, 8. Those are the nibbles. So let's see that. So 1, 2, 3, 4, 5, 6, 7, 8, all zeros. So base address is 8 zeros in hex. So now we are interested in knowing the CPL of this particular segment descriptor. So we have seen that RPL is always equal to CPL in Windows. But let's verify that. So RPL is 0, 0 in the card segment. We have seen that. So let's try to see the CPL of this particular descriptor. So that is 1, 2, 3, 4th nibble. So the middle 2 bytes of the 4th nibble, 13th and 14th. So if you do a dot format 9b, you'll get this value. So this is the 13th and 14th. So this is the highlighted value is this particular CPL. So we have proved that CPL is also 0 0, and this card segment is privileged card segment. So I'm going to press G here. So I'm letting the debugger go, and what I'm going to do is I'm going to go to the Windows 8 VM. So we have the Windows 8 VM, and I'm going to start a command prompt just as a debuggy. So this command prompt is the debuggy, and I'm going to start a usermod debugger. I'm going to attach to that command prompt I have just created. The conf host is okay, so I'm going to attach to that conf host. Any usermod process is okay for this purpose. Just I want to see the card segment value in usermod. I'm going to press the same command R here. So if you look at, we got a different card segment value, which is 1B. So let's try to analyze this card segment from kernel mode. So now I'm going to do the same thing with the value obtained from user mode. So dot format this particular value. So if you observe, you can see that the RPL is 1 1, which means that 1 1 in 1 1 in binary is 3. So this is definitely user mode. So you can see that. Again, this is pointing to global descriptor table. This value is 1 1, which is 3. Previously it was 1, now it is 1 1. Now again, if you execute that particular same command, which is just for convenience, I'm going to execute it again. So this is the 0th, 1st, 2nd, and this is the 3rd one. So this is the value in, or this is the descriptor in global descriptor table which this particular card segment is indexing into. So this is the 3rd one. If you look at this particular value, there is only one difference between the previous value which we analyzed and this one. So all we're going to do is try to understand the difference between 9 and F, which means it's just the 14th and 13th and 14th bit. So again, dot format 9, which was a previous value, dot format F. So if you look at, this is the only difference. So just 2 bytes is the difference. So this was the previous value, the 14th and 13th and 14th bit. So this value is 1 1. So those are the only difference between these two descriptors, which is the current privilege level. The current privilege level of this particular descriptor is 0 0, which is this, and this particular descriptor which we got it from user mod is 1 1 1. So there is a command to automate the process we have done so far. So we were doing the raw memory dump to understand things. This is not a very well-known command as far as I know. I've not seen a lot of people using this. So the command is dg. So dg, then the card segment, whatever value is in the card segment. So what was the value in the card segment? Using the R we can get, so it is 8. So dg 8. So we got the base of the descriptor. This is the limit. So the limit, we have seen 5FF. So there is a G bit associated with it, which multiplies the limit to 4 GB. Then this is the privilege. This is the CPL, this PL. So that is 0. So if you do a DG 1B, if you remember correctly, the one from the user mod. So DG1B, you will get pretty much everything same. Everything else should be same because every other bit was same. So this is the difference. So the privilege level is the difference. So Windows uses two card segment register values, which is 8 and 1B for kernel mode and user mode respectively. So now let's go back to our slides. So now let's discuss about the summary of segmentation. Both the card segments Windows uses as base 0 and limit 0x follows 8FFF, which is 4 GB. So this configuration is called flat memory model. So the segment has the maximum limit. Even in CPL equal to 3, card segment can access entire 4 GB. But that's not the case in Windows, as we're going to see later. Basically, there is something called honor bit in the page table entry or page table directory entry, which controls this access. So segmentation is just one part of the security, which determines the current privilege level of the code segment or the privilege of the currently executing code. As we have hinted earlier, the value in the code segment cannot be changed from a less privileged CPL than 0. So only certain instructions in CPL 0 or kernel mode can change the value of card segment. By design of Windows, segmentation does not impose any requirement or any restriction on what privileges need to access a memory block. But paging does that. This is pretty much the same statement we have seen earlier. Segmentation is one part of the security, which determines the CPL. We also didn't discuss how memory access is done via segmentation. The segment colon offset format, we didn't discuss that. Why we didn't discuss is because in flat memory model, segmentation does not contribute anything to the final physical address, but paging does that. So segmentation does not provide any changes, or segmentation doesn't change anything in that particular address. As a bottom line, in flat memory model, segmentation just provides the current privilege level of the code which is being executed. Also, there is something called descriptor privilege level or DPL, which we didn't discuss. Descriptor privilege level comes into picture only when you access one segment from another segment. We don't have that either. At any point in time, there is only one segment, which is a 4 GB segment in Windows in flat memory model. So there is no case of DPL coming into the picture, or DPL is always equal to CPL. So now let's discuss about paging. So as mentioned earlier, CPU starts in real mode. Setting the first bit of CR0 will turn on segmentation or protected mode. Setting the last bit of CR0 will turn on paging. Once the last bit of CR0 is set, irrespective of which privilege level, kernel or user, no software instruction can directly access physical memory by any means. So this is very important. So even privilege level 0 cannot access physical memory. So why is that? Because the memory address given by the programs are translated by the CPU. Translated to what? The memory addresses given by the programs are called virtual addresses, which are translated to something called physical address. Both physical and virtual address spaces is divided into chunks called pages, each of which have something called page table entry in a table in physical memory called page table. CPU uses page table for translation from virtual address to physical address, as I mentioned before. Input to the translation process is a virtual address and output is a physical address. This adds a slight performance hit, but this process enables CPU to implement virtual memory and security. So what is a virtual address? Any address which a program is giving to CPU once the paging bit in the CPU is turned on. For example, void main int a equal to 100. This is a small C program. Int star p equal to ampersand a. In this case, a is a variable and we are assigning 100 to it. So the ampersand a, or the address of a, is a virtual address. It's a 32-bit number and it's a virtual address. Now when you access that address, say for example, next instruction is star p equal to 200. That particular address is translated by the CPU to physical address before doing the access to the physical memory. So in the above example, the variable p, or the pointer variable p, contains a virtual address. All the addresses a program is using is virtual address. Now let's try to understand what is physical address. The actual address in the physical memory. So you have the RAM chip, the chip which is connected to the motherboard of the computer. So the physical address is the address of each memory location inside that chip. Physical address is a binary number CPU generate in the bus or the wires connected to the memory chip to fetch the data into CPU. This address is useless to program as programs have no access to physical memory once paging is turned on, as I mentioned. Whatever address we are giving to the CPU, it will translate into, or it will try to translate into, physical address, thinking that what we are giving is virtual address. So once the paging is turned on, whatever CPU receive from a program, say for example move ex comma some address, so CPU thinks that that particular address is a virtual address and CPU try to translate that address internally using the page table into physical address. So there is a little bit of difference between bus address and physical address. So in x86 platform it's kind of one and the same. In certain platform it's different. So there is an API called HAL translate bus address. We're going to discuss that later. So now let's think about page table. So CPU uses page table for translating virtual address to physical address, as I mentioned. Each row in the table is called page table entry. One column is virtual address of the page, one column is physical address of the page, one column is flag bits. You can think the index of the table as virtual address because the lookup happens on the virtual address, although in reality it is normally arranged as a B tree in the memory. Two very important information present in each entries of the page table in the flags column are if the current CPU mode has privilege to access this page and if the current page is present in RAM of the system or not. So this is very important. So we're going to concentrate on the first point, if the current CPU mode has privilege to access to this page or not in this particular presentation. The second point is related to virtual memory implementation and page fault handling, which is not going to be our topic of discussion. So this is the logical diagram of paging. So this is our program hello world.c, which is also loaded into the memory, into the RAM. So this is also somewhere here inside the RAM. So the program generates a virtual address. So it's giving a virtual address to the CPU through an instruction. So this is CPU getting a virtual address. Now CPU has access to physical memory. So this is the page table, which is also in the physical memory. So page table is somewhere here. This particular table is somewhere here. So using the page table has corresponding translation entry here. So we'll get the physical address, access the physical memory, and get the required page. We have the program, page table, the actual page which is being accessed. Everything is inside the physical memory. The address given is virtual address translated by the CPU using the page table to physical address and accessed through the bus of the CPU. So CPU is directly connected to RAM through bus. So this is a bus. TLB. TLB is a subset of page table which is accessed frequently and is cached by the CPU for fast translation. So this cache is called translation look-ahead buffer of TLB. So this is a bit of optimization for the translation. Page of memory. A block of memory to which you can apply protection on one page table entry in the page table per page. So each page has a page table entry in the page table. That particular page table entry bits will determine the attributes of that particular page. Size of the pages varies in 32-bit. Windows uses 4 MB and 4 KB. Following are some of the factors which determines the size of the page. So each page table entry is like a manager in a team, where the team members are the bytes in the pages. So large page is like many people are reporting to the same manager. Problems, very difficult to take care of the interest of each members. Same set of rule, which is the page table entry attributes, applied to all the members of the group. It may not fit for all the members. That's a problem with large pages, say for example 4 MB. So now what is the advantage of large page? Only one manager is needed for so many people. So we can save so many managers' salary, which is the page table entry. So we can save memory for so many page table entries. Managers' salary can be saved. Which is the page table directory entries, and the page table entries can be saved. Now small pages are like less number of team members for a manager. Advantage is people in the similar project and trades are grouped. Better match for individual interests with the interests of the team. Problem with small pages: more number of managers or more number of page table entries are needed, which takes more memory. In Windows, mixed size are used. So some of the binaries like NTOS, kernel, etc. are loaded to 4 MB pages. They are static and never paged out. Most other regions, as I mentioned, are 4 KB. So now let's have a concrete discussion, bit by bit discussion on paging. Before turning on paging bit in the OS, it should create the page tables. Because before turning on the paging, the OS or the system software has access to physical memory. The page table entries reside in the physical memory. Once the paging bit is turned on, CPU will start looking at the page table and try to translate the virtual address to physical address using the page table. So before that, the page table should set up. So one more thing both Windows and Linux does before turning on paging is making a physical memory layout. Windows, it is called PFN database. We will discuss PFN database in a later presentation. As I mentioned earlier, practically the page table is arranged as a B-tree structure. not exactly as a table for performance reasons. So you don't have to know about B-tree, or if you're not aware about B-tree algorithms, don't worry about it. So that's what we're going to explain later. So this is the 32-bit address or virtual address coming from a program to the CPU. So our input is this particular address. We have one more input for the translation called CR3 register or page table directory base address. So adding the first 10 bits of your virtual address and the current value of CR3, you will get something called page table directory entry, which is inside the page table directory. So page table directories again consist of 32-bit entries, different 32-bit entries. So one of those entries is obtained by adding CR3 and the first 10 bits or the MSB 10 bits of your virtual address. Now if you add the page table directory entry and next the middle 10 bits, this next 10 bits of virtual address, you will get something called page table entry inside the page table. This is again a 32-bit number. So this page table entry will point to a page in the physical memory. So still we are pointing to a page in the physical memory, not the byte we are trying to access. To obtain the byte we are trying to access, we need the last 12 bits of the virtual address. So if we add that 12 bits to the page table entry, we will get the byte inside the physical memory. So my explanation was not completely concrete. So there are a couple of complications in this translation. So one of the complication is all of these addresses are physical addresses, as I mentioned. Also at the same time we are not using the first 12 bits of these addresses. So first 3 nibbles, if you will, we are not using. So this addition operation is performed with the MSB 20 bits. Or the first 5 nibbles. I will once again explain in a little bit more concrete manner how the translation is done. So this is the virtual address coming from the program, any program, once the paging subsystem is turned on. Adding the first 20 bits of CR3 plus the first 10 bits of the linear address or the virtual address will fetch you the page table directory entry in the page table directory. Page table directory entry is a pointer to the page table entry along with next 10 bits of the virtual address. So adding the first 20 bits of page table directory entry with the 10 bits, middle 10 bits of virtual address will lead us to the page table entry inside the page table. Page table entry points to a page in the physical memory. If we add the first 20 bits of page table entry with the last 12 bits of the virtual address, you will get the physical address of the page, which is the output of the translation. Still, you may have a couple of questions on this translation. So what we're gonna do next is we're gonna do a live translation using WinDebug and see how things works. So unfortunately, we cannot use VMware VM player for address translation because the virtualization layer of the VM infrastructure, in this case the VM player, virtualize this part of the processor. So instead of using VM player, what we have is a memory dump of a real computer, real hardware computer. So I'm gonna use this memory dump to show you the address translation. So now, to start with the address translation, we need a virtual address. So what I'm going to do here is I'm going to type the command bang pcr. Why I'm typing this particular command is just to get an address to translate. So why I chose bang pcr is there is very less chance that this particular data structure is paged out. In this case, what I'm going to do is I'm going to take the current thread. This is the virtual address we are going to translate into physical address. So we have calc and notepad. Calc is for the calculation of hex and binary. Notepad is to remember things. We have something called scratchpad as well in WinDebug, but I like using notepad. I have copied this address to notepad. Now using the command dot format, I'm going to get the binary equivalent of that particular address. So this is the binary equivalent of this particular address. So now what I'm gonna do is I'm gonna take the first 10 bits. So this is the first 10 bits. So this is the next 10 bits, and this is the next 12 bits. So I'm gonna combine them. So these are the indexes to the table. So this is the page table directory index, this is the page table index, and this is the page index. So this will define which particular byte in a page this particular address is pointing to. So now what I'm gonna do is I'm gonna find the value of RCR3. So everything starts from CR3 register. So RCR3. So RCR3 is the CR3 register, and from where this particular address translation happens. CR3 contains physical address of the page table directory base, not the virtual address. So now the first 10 bits is an index into the page table directory. So this is the base and this is the index. Now the index we have to multiply by 4 because it is a number of D words. So we have to make it into number of bytes. So for that we're gonna use calculator. We can use WinDebug as well for this calculation, but to make things visibly clear, I'm using calculator. So now I'm translating into hex star 4 equal to 81C. The command to dump out the physical memory is bang dz. So 185. So this 185 will come here. And this 81C, which we have seen as the result, will come here. So we got something here. So this particular entry is the page table directory entry. So this is pointing to the page table. So again, this 19A, that is what is important for us. So we discard this particular value for the time being. I have to add the next 10 bits. So I'm going to do a Control C again, going to my calculator, in binary mode, Control V, moving to hash, multiplying by 4, so 5CZ. So that's what I got. So bang DZ 0019A 5ZZ. So this entry is potentially my page table entry. So this was my page table directory and this is my page table entry. Now what should I do with this? So if I add the next 12 bits, so next 12 bits to this particular value here, I will get a physical address. So let's see that. So this 12 bits, it's easy to guess from this. This 12 bits is same as 240. In this case, we are not multiplying it with 4 because it is a number of bytes. So what we're gonna do is we're gonna put 240, which is exact same as this because we are not multiplying it by 4. 240 copy bang DZ so 240 Control C Control V. So this is the physical address of the virtual address we have been translating. So let's prove that. So this is the value in this physical address. Now what was a virtual address? So this was a virtual address we were translating. So now let's try to do a DC on that address. So DC is a dumb character for a virtual address. So we are getting the same thing. So we were leaving 12 bits up here and up here. So we assumed that when we did the translation, we assumed that they were not there at all. Those values were 00. So that's why we did the calculations. So these bits are very important. So these bits are the flag bits actually in the page table entry. So if you do a dot format, so these are the flag bits. This is the 12 flag bits are there. So these are the 12 flag bits. So we will see the importance of this bits later. So now there is a command to automate the process we have done so far. So that command is called bang PTE. If you give bang PTE and the virtual address, it will give you the translation. If you look at this carefully, this is the page table directory entry. So 19A, so we got it here, 19A. This was all page table entry, so we got it here. So this address, if you look at this, these addresses are different from what we looked at. They are not the addresses we are looking at. So these addresses are coming from the fact that all the page table directory databases are mapped into the kernel mode address. So certain APIs like get physical address, etc. uses this mapped version of page table or the page table directory, page table entries to convert into physical address. According to me, this is not the correct way of translation. This is not the way processor do the translation. Processor do the translation in the way which we have discussed, not using the mapped pages, because at the time of translation processor does not have access to virtual address space. Processor has access to physical address space. It needs the tables in the physical memory, in the physical address space. So this is a Windows specific thing what I'm talking about. If you look at Linux or some other operating system which is running on x86, things could be different. So but still you can use bangpt command to understand the final physical address. Final physical address of the byte you have given is this 5 digits and this 3 digit. That will be the final physical address. That's how you interpret the bangpt command. So bangpt also resolved the flag bits. So 2 flag bits are important to us. One is this and one is this. So this is the valid bit, this is the user or kernel mode bit. So this is the first and this is the third. These two are important for us. So now let's go back to our slides. So we have seen these commands. DC is used for dumping out the content of a virtual address, the values in a virtual address. So dump character in a virtual address. bangtc or the variations of bangtc, bang d star, is used for dumping out the physical memory content. So if you're giving a physical address, it will dump out the content of that physical memory. Very useful command, very rarely used as well. So bangpt is the command which automates the translation. So if you give a virtual address to bangpt, it will translate into the physical address, will show you the page table directory entry, the page table entry, etc. So now let's discuss about page table entry format. So we have seen that the MSB 20 bits, or the first 5 digits in the hex, is pointing to the physical page, but it's a 32-bit entry as we have seen. So we have 12 bits free. So first 20 bits we are using it to point it to a page in the physical memory. So now let's try to understand what is the next 12 bits. So they are called flag bits. We are going to discuss only 2 flag bits. One is the first bit and another is the third bit. So first bit is the valid bit, which will say that the page is present in physical memory or page is present in the page file. So we'll have a detailed discussion on that later, not in this presentation. In this presentation we're gonna concentrate on the third bit. So honor bit or kernel mode or user mode bit. So these are the list of other bits which we are not going to discuss at this point in time. So this is where our discussion is going to complete on the privilege check. The current privilege level is determined by the CS register, as we have seen before. To access a page with third bit in the PTE not set, the current privilege level of the code segment should be 0. So this is very important. So if the third bit is not set and the current privilege level of the code segment is not 0, you will get an access violation. So if above bit is 1, page can be accessed from any CPL including 3. So that is another point. If the third bit or the user bit is set, which means that the page is a user mode page and can be accessed from any privilege level. So now how is this implemented in Windows? In Windows, out of the total 4 GB addressable space or the 4 GB segment, the upper 2 GB of all the pages has the third bit not set, or the third bit in the PTE is 0, which means to access those pages the CPL should be 0, which means that the processor should be running in kernel mode, or the code segment RPL should be 0 or CPL, both are same. So the upper 2 GB is called kernel address space or privileged memory region. So this cannot be accessed from any other rings other than CPL equal to 0. This is Windows specific, and it is the OS developer or the OS designer decides how much pages needs privileged access. It can be 4 GB, it can be 1 GB, it can be one page, anything. So for example, in Linux it's different. In Windows there are two modes. /3GB mode, there is only 1 GB of kernel space. So that depends on the design of the operating system. Windows keep all the OS related data structures in this region of memory. So because this region is not accessible from CPL equal to 1, 2 or 3, which means that user mode cannot access this particular data region. So application like Notepad or a web browser does not have access to this region as it is running in privilege level 3 all the time. If they try to access, they get an access violation, and that access violation is handled in privileged mode, mostly to terminate the application. The lower 2 GB, which is 002 7 follows 7FF, has all the pages in the PTE has third bit set to 1, which means they can be accessed from any privilege level 0, 1, 2 or 3. This part of the address space is also called user mode address space, where any application like Notepad or Word or anything else can access and run and keep their data. So this is a very important point. Neither PTE, the page table entry, or card segment can be changed from user mode. To change page table entry or card segment, you have to run in privileged mode or ring 0 or CPL equal to 0. So now what we're going to see is we're going to see the third bit of a page table entry in a user mode address and a kernel mode address. So this time I'm going to use the command bank process 00 to get the details of a user mode process. So I got task manager running while the dump was taken. Dump was taken by notmyfault.exe. So I'm going to select this particular process and I'm going to switch into that process. Dot process /r/p. Don't worry about the switches if you're not familiar. So all I am trying to get is a valid user mode address. So I got a warning, I don't care. So I'm going to type the bank peb. See if we can get a valid user mode address. So I'm going to do a bank PTE on this address just to see if it is valid. Yeah, it is valid, so we'll go with this address. I'm not going to do the translation as I did before just to save time, but I'm going to stick with bank PT and assume that bank PT is correct. So what you can do is you can do the translation yourself if you're not convinced. So all I am interested is this 3 value. So this is my page table entry we have seen. So all I am interested is this 3 digits, which is the 12 bits of the page table entry. I'm going to do a dot format on that. So in this case the third bit is 1, which means that this page is user mode. This page can be accessed from any privilege level. This particular page can be accessed from any privilege level. So this bit is 1. Now let's try a kernel mode address. So for a kernel mode address, I'm going back to the command .pcr just to get a kernel mode address. So this is a kernel mode address. So I'm going to do a bank PT on that address. So I got it kernel mode. So still I'm going to do a dot formats on that. So I got that bit 0. So which means that this is a kernel mod address, or this is a kernel mod page. This page can be accessed only if my CPL equal to 0. So you can check with other pages as well. You should find the same result. Now let's go back to our slides. So how the switching happens between privileged and non-privileged segments. So we have seen two segments. One is the non-privileged segment where the CPL equal to 3, and the privileged segment where CPL equal to 0. So from privileged to non-privileged, things are very easy. Just change the chord segment. The reverse switch happens via something called software or hardware interrupt. So for example, execution or access of any privileged instructions or memory respectively. So all the exceptions are handled in kernel mode. All the interrupts, whenever it happens, either it is software or hardware, the processor will switch into kernel mode because the handler is in kernel mode. Instructions like sys enter, int2e, int3, int xx, any interrupts for that matter, all are handled in kernel mode. So whenever this kind of instructions comes into the execution from user mode, the control is automatically transferred into kernel mode to a specific location, not to some random places, to some specific location where the OS programmer has installed handlers, interrupt handlers. So it's like a 911 emergency call. You're calling the police and you have a specific special handling situation. Ideally, the security cannot be compromised in this transfer because we are executing specific handlers from the operating system. We are not executing any user mode code by switching into the kernel mode. So there are a couple of things more we have to discuss, so I'm not going into the details of them. So following 6 instructions has some additional security checking over the checking we have discussed so far. CLI, clear interrupt, set interrupt, in-s, out-s. All these 6 instructions will check additional bits in the E flags called IOPL. To execute the above instruction, the current privilege level of the code should meet or beat the IOPL, which means numerically CPL should be equal or less than the IOPL bits in the E flags register. In Windows, the IOPL, the IO privilege level, is always equal to 0, which means to execute above 6 instructions you need to be in kernel mode or your CPL should be 0. We have discussed the security between kernel mode and user mode, between the operating system and the application. How about between applications? There is a good chance that you will get confused if you are reading the processor manual. So what Windows has done is every process has its own CR3. When the process switch, all Windows is doing is switching the CR3. So when the CR3 changes, the page table directory base address changes, which means that all the translation schemes changes. So once the CR3 is changed, it's like a whole new page table is loaded. So the translation changes accordingly. For all the page table, the upper 2 GB is mapped to the same physical address which is common to all processes, which is the kernel address space. That's why we say the upper 2 GB or the kernel address space is common to all the processes, because it maps to the same physical address. But the lower 2 GB may or may not map to the same physical address. If you are referring to the private bytes in the user mode, it'll be mapping to a different physical memory, either in page file or in RAM. We'll see that in the demo. So now we are going to start with the same command which we have executed before, bang process 00. So this command is helping us to access the user mode address of different processes. So these are the two processes we are going to look at. Take an address and translate the same address in both the process address spaces and prove that they are pointing to different physical memory. So this is a valid address in both address spaces. So first what we're going to do is we're going to switch into the context of this process. So the command is dot process slash r slash b, the process pointer. Now I'm going to do a DC on this particular address just to see what is inside that address. So this is a value inside that address. Now I'm going to do a bang PTE on that address. So I got this physical address. So this is the address of the page in the physical memory. Now I'm going to switch the process to the second one. So the command is same with the different process pointer. Now I'm going to execute the same commands. So DC on the same address. So as you can see, the value is different. This value is not this value. So we got a different value for the same address. So this is same. The address is the same. Now if I do a bang PTE on that address, this address, I should get a different physical memory. So this value is different from this value. That's why we are getting different values here and here. Which means that when the operating system is in the context of task manager.exe, this particular virtual address is pointing to a specific physical address which is different than when the operating system is in the context of notmyfault.exe. It's just the same virtual address, but the physical address is different. When the process context changes, the physical address changes, which means that it is accessing two different memory. So that is how the isolation between these two processes are achieved in the operating system. So if you can look at carefully, you will see the directory base address is different. So that is the main thing which is changing when the process address base changes. Now let's go back to our slides. So following are the three Windows kernel mode APIs worth mentioning in this particular discussion: mmmap IO space, mmget physical address, and HAL translate bus address. HAL translate bus address is not very much related to the discussion, but I got a couple of questions regarding this particular API when I was doing this presentation before, so I thought of including this as well. So mmmap IO space. Mmap IO space is you have a couple of physical address which you wanted to map to virtual address. Mmap IO space, input is physical address, output is virtual address. Mmget physical address is just the opposite of it. You have a virtual address and you need the physical address. So mmget physical address is pretty much like the bang PTE command which we have seen. mmap IO space will generate PTEs or page table entries and give you the virtual address equivalent to it. mmap IO space create page table entries for physical pages. So we'll see the first two APIs in action. I'm going to get a valid virtual address from mmap IO space, which is supposed to point to this particular physical address, and I'm going to assign 100 into that address. So I'm going to successfully dereference that particular pointer, and I'm going to access that memory. Here what I'm going to do is I'm gonna get the physical address equivalent to this particular virtual address. So potentially I should get 1234 in the OPT physical address. OPT physical address is the output of mmget physical address. So mmap IO space take three parameters. One is the physical address, which you want virtual address, then the number of bytes, then the memory caching type, which I'm not going to discuss here. Get physical address is very straightforward. It just take the virtual address and it gives the physical address as output. So this is a driver which is running on my Windows 8 VMware box. So what you are seeing currently is the window of Visual Studio 2010. So this is running on Windows 8 virtual machine. I got an ASM int 3 here just to break into the debugger when this particular function is getting executed. So this function is the driver entry of ioctl sample in DDK. I just wanted to execute this particular functions in kernel mode, so I just selected a random function, random driver, etc. So all we're going to concentrate is this particular lines. So I'm going to minimize Visual Studio and I'm going to load this particular driver. So I have broken into this int3 statement, which is the debug breakpoint in the driver. So the VM is completely hung because it is attached to the debugger at the moment. So it's being debugged. So I'm going to press F10 to step over. So this is just the driver entry code of the driver. This is IO create device, etc. So that's not what we are interested. This is what we are interested. So I am going to assign the high part to 0 and low part to 1 2 3 4. So let's see the physical address now. dt my phyAdd. So this is how it looks at the moment. The chord part is 1 2 3 4. This is also 1 2 3 4 because the low part. So if you do a dot format, you'll understand that. So this is also 1 2 3 4. So my PTR is a valid address in the kernel mode, so A53FC42. So I successfully executed that particular statement. Dereferencing is okay. Now what I'm going to do is I'm going to call get physical address with the pointer which I got from map iospace. At this point in time, let me dump out the output physical address, my opt phyAdd. So in this case I have initialized it to 0, nothing so far. I'm going to press F10 and going to execute the same command. So I got 1 2 3 4, which is the one I have given here. This is kind of complementary APIs, map iospace and get physical address. Now we are left with the HAL translate bus address. Basically this is an obsolete API, as I mentioned before. So this is not currently being used, although Windows internally uses this API. The fact is that this API doesn't do much in an x86 platform. In x86 platform, physical address is the best address. In certain platforms, these two addresses, the best address and the physical address, is different. In certain type of buses, like PCI, etc. In those cases, Windows reaches into an agreement with the chipset which implements this particular bus protocol, say for example PCI, and translate the bus address and physical address to and fro. Bottom line is, in x86 platform, in most of the buses, as far as I know, physical address is same as the base address. So this particular API doesn't do anything in x86 platform. You can prove this by using this API. or you can look at the reverse engineered code. If you look at the assembly, this is a very simple and straightforward implementation. Only path differs is a PCI, and you will ultimately find out that the PCI is also doing nothing in x86 platform. Little bit about page fault handling. We are not going into the details of it. If the V bit of the page table entry is not set, it means that the page is not in the memory, but it's in the page file. CPU treats this as an exception or interrupt or page fault, if you will, and transfer the control to a predefined page fault handler, which is normally in CR2 register. A handler does is read that particular page from the disk and store it in the memory, and let the CPU restart the instruction which causes a fault, so that it will be transparent to the application which uses that particular instruction. So here are some of the final Q&A. Why we cannot access other process memory directly? So one CR3 and one segment of 4 GB at a time. CR3 register is unique at a time, so which means the page table translations are unique at a time, which means one process equal to one CR3. So at any time, only one process address space is active. So there is no other process address space to access at that point in time, because that particular CR3 is pointing to that particular process address space. When the context switches to a different process address space, as we have seen before, the CR3 register changes and the translation scheme changes, and the translation changes to a different physical memory. So how do we get a common kernel model space? The upper 2 GB. The system page table entries are same for all the processes, which means the upper 2 GB pages maps into the same physical memory. Now, what about inter-process communications? This is done by either mapping the same physical address to different virtual addresses, or sharing with the kernel address space, which is also common to all the process address spaces. Anyway, it is different virtual address map into same physical address. So what happens when we touch a kernel mod address from a user mod? So we'll get an exception and it switch into the kernel mod. How physical memory is used by a DLL like NTDLL is not replicated, although it's being used by all the processes. Again, the same mapping principle, same physical memory is mapped to different virtual addresses in different process address space. So that's all. Thank you very much.